Now we're going to do some mixed practice problems. And these are going to be tough because we have a lot of formulas in this unit. All right, now what if we want to sketch electric field lines? Let's see if I have a negative charge. Remember, it always starts on positive, ends on negative. And for a negative charge, it's going to be radially inward. Now, if I tell you to give me 10 arrows, you give me 10 arrows. I'm only going to put 8 here. Now, what if you have a positive charge? It doesn't matter that this is 3.4 times 10 to the negative 6. It's going to be going out, radially outward. All right. What if you have a positive charge and a negative 2 charge? Now, this one, positive 1 coulomb and negative 2 coulombs. Now, you do kind of have to put the signs and magnitudes on this one because this one's going to have twice as many arrows as the positive one because its charge is twice. So just go in and put in just a couple. Always have the one going straight out and straight in. And let's see, this is going to curve. So, all right, now we need twice as many on this side as this side. So I have 1, 2, 3, 4, 5, 6. So I need to add in 1, 2, 3, 4, 5, 6 charges. Now this is a dipole. A dipole has a positive and a negative. It always starts on positive and ends on negative. So always have the one going straight out and straight in. And then, which I suppose we should connect these, shouldn't we? All right, like that. All right. What's the magnitude of the electric field where a positive charge of 5 times 10 to the negative 6 coulombs has a force of 0.7 newtons? So I have Q is 5 times 10 to the negative 6 coulombs. F is 0.7 newtons. I know F is QE, and I'm looking for E. So I divide both sides through by Q. So the electric field is the force divided by Q. So it's 0.7 divided by 5 times 10 to the negative 6, or 1.4 times 10 to the fourth newtons per coulomb. Now I'm looking for the magnitude of the electric field, so I'm looking for E. Oh no, magnitude is 4.2 times 10 squared newtons per coulomb, and the force is 0.9 newtons. How many coulombs does positive charge have? Well, E is equal to 4.2 times 10 squared newtons per coulomb. By the way, you can write this as 420 newtons per coulomb, 420. F is 0.9 newtons. So F is QE. I'm looking for Q, so I divide both sides through by E. So the Q is the force divided by E. So the force is 0.9 newtons divided by 420 newtons per coulomb. Or I get a charge of 0.00214 coulombs. What is the electric field? Okay, so I'm looking for E of a charge Q of 3.6 times 10 to the negative 15 coulombs that has a force F of 5 times 10 to the negative 3 newtons. All right, Q is 3.6 times 10 to the negative 15 coulombs. F is 5 times 10 to the negative 3 newtons. And I'm looking for E. And I know F is QE. So I want to solve this for E by dividing both sides through by Q. E is F divided by Q. The force is 5 times 10 to the negative 3. Ooh, that's a 3. It only looks like I wrote a 6. Just kidding. 3 newtons divided by 3.6 times 10 to the negative 15 coulombs. So divide those two, you get 1.389 times 10 to the 12 newtons per coulomb. Now a test charge experiences a force F of 1.4 times 10 to the negative 8 newtons at a point where the electric field E is 2 times 10 to the negative 4 newtons per coulombs. What's the charge? All right. F is 1.4 times 10 to the negative 8 newtons, and E is 2 times 10 to the negative 4 newtons per coulomb. I want to find Q. I know F is QE, so I want Q, so I divide both sides by E. Let me do this up here. So Q is the force divided by the electric field. The force is 1.4 times 10 to the negative 8 newtons, and the electric field is 2 times 10 to the negative 4 newtons per coulomb. So you wind up with 7 times 10 to the negative 5 coulombs. Now assume the field is created by a negative charge. All right. What is the direction of the field on the test charge? Well, my test charge is always positive, so it's going to be towards the center of the field. Now electrons are accelerated by an electric field. Find the force on the electron. Okay, let's see. So I have Q is negative 1.6 times 10 to the negative 19 coulombs. And I know that E is 10 to the 5th newtons per coulomb. Find the force. F is QE. Q is negative 1.6 times 10 to the negative 19. E is 1 times 10 to the 5th newtons per coulomb. So I get negative 1.6 times 10 to the negative 14 newtons. And what that negative sign means, if my electric field is going to the right, then the force on my negative charge is to the left. The electric field is produced by a positive charge. What's the direction of the field on the electron? It's going to be opposite. A uniform electric field has a magnitude of 250 newtons per coulomb. A 12 microcoulomb charge moves 0.2 meters in the direction of the field. What's a change in electric potential energy? All right, let's write out your givens. I have an electric field of 250 newtons per coulomb, and I have a charge Q of 12 times 10 to the negative 6 coulombs, and a distance traveled of 0.2 meters. And I want to find the change in potential energy. So I know the change in potential energy is minus QED. So the charge is 12 times 10 to the negative 6, and don't forget your negative sign. And my charge is positive, so I'm good. My electric field is 250 newtons per coulomb. And the distance it travels is 0.2 meters. And it's in the direction of the electric field, so I'm right there. I've got my positive distance. So this is negative. When I multiply through this out, I get 6 times 10 to the negative 4 joules. So my charge will lose 6 times 10 to the negative 4 joules of potential energy. What is change in electric potential energy? So I'm looking for change in PE. In a lightning bolt, charge Q is 35 coulombs. D is 2,000 meters. And the electric field is 10 to the 6 newtons per coulomb. All right, so Q is 35 coulombs. D is 2,000 meters. And E is 1 times 10 to the 6 newtons per coulomb. So the change in potential energy is minus QED. The charge is positive 35. The electric field is 1.0 times 10 to the 6 newtons per coulomb. The distance is 2,000 meters. So this is negative 7 times 10 to the 10th joules. A charge moves a distance of 2 centimeters. So D is 2 centimeters, which is 0.02 meters, in the direction of a uniform electric field that has magnitude of 15. So E is 215 newtons per coulomb. The change in electric potential energy is negative 6.9. So the change of PE is negative 6.9 times 10 to the negative 19 joules. Find the magnitude of the charge. So I'm looking for Q. All right. I know the change in potential energy is minus QED. I'm looking for Q, so I'm going to divide through by negative ED. So the charge is negative change in potential energy divided by ED. Remember, it doesn't matter whether the negative sign goes in the numerator or denominator. So let's come on up here. Q is minus, let's see, the change in potential energy is negative, so put that negative sign in there, 6.9 times 10 to the negative 19 joules, divided by E, which is 215 newtons per coulomb, times D, which is 0.02 meters. Now, negative times negative is positive, so you get 6.9 times 10 to the negative 19 in the numerator. Remember, go ahead and multiply 215 times 0.02 to get 4.3 in your denominator. And now do your division. So you get a positive 1.605 times 10 to the negative 19 coulombs. All right, if 120 joules of work is done to move 1 coulomb of charge, what voltage exists? Let's see. The work is going to equal the change in potential energy, which is 120 joules. Q is 1 coulomb. Now I know that there's a relationship that is the definition of electric potential, which is the change in potential is the change in potential energy per unit charge. So this is going to be 120 joules divided by 1 coulomb, or 120 volts. All right, a voltmeter reads 500 volts when placed across a charged parallel plate. The plates are 0.02 meters apart. What's the electric field? V is 500 volts, and D is 0.020 meters. Now I know the change in potential, sorry about that, the change in potential, or V, for parallel plates is going to be ED. So I'm looking for E. I divide both sides through by D. E is V divided by D. So it's 500 volts divided by 0.02 meters, or 2500 newtons per coulomb. Well, didn't mean to do that. Sorry. Now, if I have a uniform electric field between two parallel plates is 1050 newtons per coulomb, and the voltage is 100, how far apart are they? So I have E is 1050 newtons per coulomb. V is 100 volts. How far apart are they? I'm looking for D. And I know V is equal to ED. So D is the voltage divided by the electric field. So this is 100 volts divided by 1050, or 0.095 meters. Now, if I have a 2.02 Coulomb particle having a force of 40 newtons, what's the strength of the electric field? Well, let's see. We have Q is 0.02 coulombs, and F is 40 newtons. I'm looking for E. What's the relationship between force, Q, and E? Well, I know the force exerted on a charged particle is going to be the charged particle times the magnitude of the electric field. So the electric field, I'm going to divide through by Q. The electric field is the force per unit charge. All right, the force is 40 newtons, and the charge is 0.02 coulombs. So the electric field is 2,000 newtons per coulomb. Now, if the electric field in the atmosphere is 150 newtons per coulomb downward, so E is 150 newtons per coulomb, and that's downward. What's the direction of the electric force on a positively charged particle? Well, of course, a force is always in the direction. It would push a positive particle, so it is also downward. Of course, if it was a negative charge, it would be upward. Find the force on a proton with charge 1.6 times 10 to the negative 19 coulombs. All right, I have E is 150 newtons per coulomb. Q is 1.6 times 10 to the negative 19 coulombs. F is QE. So let's see, this is kind of hard to write at the bottom of this. 1.6 times 10 to the negative 19 times 150, or 2.4 times 10 to the negative 17 coulombs. And of course that is downward.